So I'm happy to introduce Dr. Penelope Rice. Dr. Rice has worked as a toxicology reviewer for the Office of Food Additive Safety in the USDA for over 18 years. During her time at the FDA, Dr. Rice has worked on several issues relating to the hazard assessment of food contact materials, including conducting post-market safety assessments of perfluorinated greaseproofers and formulating guidance for the toxicity testing of nanomaterials for use in food contact applications. Dr. Rice received her PhD in toxicology from the University of Rochester. She has a master's in physics from Florida State University, and she has a bachelor's of science in physics from Clemson University. Thank you so much, Dr. Rice. We really look forward to hearing your presentation.
Okay, great. So I am pleased to, let me minimize my photo here. So I'm pleased to present my talk today. This talk is based on a paper that was published in Food Chemical Toxicology in 2020. Its title is The Comparative Analysis of the Potential Human Health Effects of 6,2-Fluorotelomer Alcohol versus Perfluorohexanoic Acid. Oh, all right. There we go. So I'm going to, during this talk, I'm going to give a brief introduction, and I'm sure you already know what Pfas are, but I'm going to tell you anyway. And then I'm going to go into the material that was discussed in my paper, and then give some brief conclusions. So what are Pfas? As you already know, they are compounds consisting of or containing as a functional moiety a carbon chain straight or branched, where one or more of the carbons is partially or fully fluorinated. Now, there are two specific types of Pfas that I'm going to discuss during my talk. One is what are called perfluorocarboxylates, which are carboxylate alkyl carboxylates, where all carbons are fully fluorinated except for a carbon bonded to a functional group that is the carboxylate group. And as you can see here, perfluorohexanoic acid is the example of this compound that will be discussed, this compound class that will be discussed during my presentation. The second group of compounds are called polyfluoroalkyl substances, specifically polyfluoroalkyl alcohols. So these are, this is a carbon chain that is only partially fluorinated that is bonded to an OH group. So the example that I'm showing here is a 6,2-telomer alcohol, and as you can see at the end, there is the OH group here, and then an alkyl group, couple of alkyl groups, and then here starts the fully fluorinated chain. And the significance here of this is that with before, where you had the fluorocarboxylate, no metabolism can occur. Whereas when you have a polyfluorinated compound, you can get metabolism. So this can be transformed into a number of different compounds. And so if you, as one would expect, you would think, well, you know, it's possible that this particular class of compound might behave differently in the body than this compound. So, then continuing with the introduction. So long chain PFAS, these are greater than 8 perfluorinated carbons. They for the perfluorocarboxylates, and greater than equal than 6 perfluorinated carbons for the perfluoroalkyl sulfonates. Short chain PFAS, which is what I'll be discussing today, have fewer than 8 perfluorinated carbons for perfluorocarboxylates and fewer than 6 perfluorinated carbons for fluorosulfonates. They have useful properties. They are stable, very stable, or at least the non-metabolizable ones are stable. They're oil and water repellent. However, there are concerning properties for LC-PFAS as well. They're persistent in the environment and animals. They are immunotoxic, and they display reproductive and developmental toxicity, and some are carcinogenic. How are people exposed to PFAS? They're exposed via multiple routes, inhalation, dermal, and oral. They're exposed in food packaging, drinking water, dust, food contaminants. They're occupationally exposed populations. They're exposed to very high levels indeed. Dr. Kabati mentioned ski waxers. In addition, firefighters and people who work in fluoropolymer manufacturing facilities are also highly exposed. And there are some very famous highly exposed general population cohorts, like the C8 cohort that was highly exposed to PFOA from the Washington Works facility. And then the Cape Fear River Basin cohort in North Carolina that was exposed to Gen X in their water supply. So what are C6 PFAS compounds? This is going to be the focus of the talk today. These are compounds containing as a moiety a straight alkyl chain containing 6 fully fluorinated carbon atoms. Exactly 6, not 4, not 5, not 7, 6. Examples are C6 PFAS, acrylate and methacrylate monomers, and polymers made from these monomers, as well as perfluorohexanoate and the 6-2-fluorotelomer alcohol. The 6-2-fluorotelomer alcohol and perfluorohexanoate are impurities in the C6 PFAS polymer coatings that are used in food packaging, textiles, and in floor waxes. The fluorotelomer is also a metabolic byproduct of other impurities in C6 PFAS polymers, such as the monomers themselves, and possibly from the oligomers derived from these polymers. So these C6 PFAS compounds were originally intended as replacements and are used as replacements for their long chain PFAS chemicals that were used in the same uses. At the time of the authorization, the C6 PFAS had not been shown to biopersistent, thus were not considered to be as toxicologically concerning as LC-PFAS. The properties of these chemicals, in particular the 6-2-fluorotelomer alcohol and perfluorohexanoate, were summarized in Rice et al. Rice 2015. However, Russell et al. 2015 in a paper published late in the same year raised concerns for biopersistence in human tissues and animal tissues of the 5,3-acid metabolite of 6-2-fluorotelomer alcohol. Kabati et al. Emphasized these concerns and identified the 5,3-acid in particular as potentially biopersistent in rats. But Kabati et al. Emphasized the need for additional studies to characterize the biopersistence potential of the 5,3-acid. So this is the 5,3-acid. As you can see, it is a polyfluorinated compound. You would expect it to be broken down based on the presence of 2 alkyl groups in it, but apparently it is not, or it is broken down very slowly, because as Dr. Kabati's work shows, it is the most prevalent compound in serum after 6-2-fluorotelomer alcohol exposure, as we will discuss further. So here we get into the paper itself. So because of, based on Dr. Kabati's work on the 5,3-acid metabolite, that work raised questions about how similar are the toxicological effects of perfluorohexanoate and the 6-2-fluorotelomer alcohol, because the current thinking at the time on C6 PFAS toxicity was that perfluorohexanoate was a good model for thinking about how C6 perfluorinated chemicals in general behaved in the human body. And specifically, this point of view was expressed in Luz et al.'s paper as published in 2019. Direct quote, the perfluorohexanoate RFD can be used to inform public health decisions related to perfluorohexanoate and fluorotelomer precursors, for which PFHXA is a terminal degradant. So based on Dr. Kabati's work, we decided, well, let's examine if that's really true, because as it turns out, there's quite a bit of toxicological data from identical studies conducted in the same species on both compounds. So it is possible to compare side by side the behavior of perfluorohexanoate with the behavior of 6-2-fluorotelomer alcohol in identical studies in an identical species to see how exactly, how similar are they. So the purpose of the analysis that was published in 2020 was to update the Rice publication with additional newly available information pertinent to the toxicological profile of the 6,2-fluorotelomer alcohol to directly compare the toxicological profiles of perfluoroxanoate and the 6,2-fluorotelomer. And I must emphasize this was intended as a qualitative comparison only. This is not intended to be a quantitative risk assessment. And the second purpose was to ascertain whether perfluoroxanoate adequately describes potential human health effects of the 6,2-fluorotelomer alcohol via comparison of TK characteristics and apical effects and points of departure for these two compounds from the cited studies. Again, this is a qualitative comparison only. So here are the results of the analysis. So let's first look at the TK between perfluoroxanoate and 6,2-fluorotelomer alcohol. Both are well absorbed, but the similarities end there. Perfluoroxanoate is not metabolized, whereas the fluorotelomer is extensively metabolized into several different compounds. It's highly, if you look at earlier publications on the metabolism of the 6,2-fluorotelomer alcohol in hepatocytes, you get a list of probably, I would say, 20 different compounds that hepatocytes can metabolize the fluorotelomer into. The stable metabolites, perfluoroxanoate is among them, but there are others, including the 5,3 acid, the 4,3 acid, and other carboxylates. Distribution is for the perfluoroxanoate is very similar to PFOA, it's plasma, liver, kidney, whereas the 6,2-fluorotelomer goes into fat too. Excretion, urine is the major route of excretion for perfluoroxanoate, but with the fluorotelomer, it is also excreted in feces, depending upon the metabolite. Fluoroxanoate, its half-lives in male rats and male and female rats extremely short and measured in hours, whereas the 5,3 acid, as Dr. Kabadi has already discussed, is measured in days. And if you look at how the values for the half-lives compare with known biopersistent PFAS compounds, the 5,3 acid is as biopersistent in rats as Pfas in perfluorooctane sulfonate, and more biopersistent than PFOA in either mice or rats. So let's get into the apical effects from systemic toxicity studies in adult rodents. So this table summarizes results from side-by-side comparisons of the behavior of perfluoroxanoate or sodium perfluorohexanoate versus the 6,2-fluorotelomer alcohol in rats in 28-day and 90-day toxicological studies. These are standard OECD 407 and 408 studies. In addition, there was a 90-day study that was available in mice with the 6,2-fluorotelomer, where the effects were also included in this analysis. So if you look at the apical effects in the liver, you do see some similarities. You see hepatocellular hypertrophy in both and increased liver weights. You do see some increased serum liver enzymes at high doses of perfluoroxanoate, but some hepatocellular necrosis, but at very low incidences and only at high doses. In contrast, there is a marked increase in adverse liver effects with the fluorotelomer alcohol. You get hepatocellular necrosis, inflammation, oval cell hyperplasia, and biliary hyperplasia, and cytoproliferative. In mice, you get cytoproliferative lesions, including increased mitotic figures, and in male mice, a basophilic focus. So in summary, the liver effects with 6,2-fluorotelomer alcohol are both more adverse and indicate proliferation, whereas with perfluoroxanoate, you only get hypertrophy. So in the kidney, you get some increased kidney weights, but in the majority of the effects are in the liver. The kidney is comparatively spared with perfluoroxanoate, whereas you get marked kidney toxicity with the fluorotelomer alcohol, including increased kidney weights, renal tubular necrosis, basophilia, dilation, mineralization, and degeneration. And in fact, in these repeated dosing studies, adverse kidney effects are often the cause of early mortality and sacrifice for or early sacrifice for morbidity because of renal effects. These renal effects are particularly marked in the females in these studies. As far as apical effects on the immune system and thyroid, the apical effects on the immune system are pretty similar. These effects would be expected because both the 5,3 acid and perfluorohexanoate are PPAR alpha agonists, and PPAR alpha agonists are known to be immunosuppressive. So the effects listed here are not surprising. Apical effects on the thyroid, no consistent effects were found with the Fluorotelomer. We did see some occasional increased weights and follicular cell hypertrophy with perfluorohexanoate. This is likely secondary to enzyme induction in the liver, as has been seen with other compounds that are liver enzyme inducers. So points of departure. The Fluorotelomer study has generally lower NOELs for the studies under repeated dosing conditions than perfluorohexanoate, indicating a greater potency. In particular, mice have very low NOELs and LOELs. And again, these are NOELs. This is not taken into account adversity under the study conditions. But again, this indicates that the Fluorotelomer is more toxic than perfluorohexanoate under similar study when assessed under similar study designs. And if you look at the 5,3 acid, it's remarkable. This is a 2-week gavage study that was conducted in rats. The doses were 30, 300, and 900 mg per kg. For the males, the 300 and 900 mg per kg rats lasted for 4 days. After that, they were all dead. The only rats that survived the 2-week period were the male rats given 30 mg per kg. The females were more resistant. The LD50 under the conditions was 300, but still there was quite a bit of fatality. And 5,3 acid in that study was shown to be a marked peroxisome proliferator in both male and female rats. So now we're going to discuss the reproductive and developmental effects of the two compounds. So we were able to locate studies that were conducted in both mice and rats with perfluorohexanoate and the Fluorotelomer. The apical effects on reproduction, again, marked difference. There were no effects on reproduction at all in rats, and only very minor effects in mice, which was increased numbers of stillborn pups. In rats, there were marked effects with the Fluorotelomer. There were marked effects in both mice and rats. In rats, there were decreased numbers of dams delivering litters, decreased gestation index. This could have been secondary to high dam mortality. However, in mice, there was decreased maternal feed consumption and body weight gain during lactation. There were mammary gland lesions, decreased uterine and ovarian weights, and increased numbers of mycin and estrus. On development, again, you saw increased adverse effects and with the Fluorotelomer versus perfluorohexanoate. With perfluorohexanoate, the main effects were decreased weights, both prenatally and postnatally. However, with the Fluorotelomer, in addition to the decreased body weight gain postnatally, you had increased pup mortality, and prenatally you saw skull ossification delays and wavy, thick or bent ribs. Mice had both that were administered the Fluorotelomer, evidence both decreased pup survival and body weight during lactation. So very similar to to the effects noted with PFOA in mice. So comparing the points of departure from these studies, again, you see increased potency with the fluorotelomer versus perfluorohexanoate. If you're comparing the prenatal studies in rats, it's, again, the fluorotelomer is more potent. With the one generation, a reproductive study, again, higher potency for reproductive effects. In rats, again, higher potency for postnatal effects in rats, and similarly with mice. So the conclusions, to conclude, the toxicological data set for perfluorohexanoate is clearly not appropriate to assess the hazards associated with the fluorotelomer exposure. This is based on quantitative and qualitative differences in effects on livers and kidneys between rats administered the 60-fluorotelomer versus rats administered perfluorohexanoate or its salt in OECD 422 28-day, 90-day oral toxicity studies, and also due to the biopersistence of the 5,3-acid metabolite of the fluorotelomer versus rapid elimination of perfluorohexanoate. And the second conclusion is the toxicological profile of 60-fluorotelomer indicates that it is significantly more toxic than perfluorohexanoate, and that the use of toxicological studies conducted on perfluorohexanoate for risk assessment of the fluorotelomer exposure may underestimate the human health risk associated with a given daily 60-fluorotelomer exposure and fail to capture apical effects.